You're ready to go. Have a good session.
Hi. Okay. So hi, everyone. Welcome to this secret sharing session on Thursday. And the first talk is by Oded Nir and Benny Applebaum about up slices, down slices, and secret sharing with complexity of 1.5 to the n.
Thank you. So do you see my screen?
Yes.
Yes. Yes.
Okay, excellent. So this is joint work with Oded Nir, my talented student, and I urge you all to watch the full version of this talk that Oded has recorded. So, what's my content? Okay. So we're going to talk about the secret sharing schemes, which are basically distributed analog of encryption schemes. So in the general version of this problem, we have a dealer who holds a secret S and N parties or N servers if you want. And we are given a list A of authorized and unauthorized coalitions. And the goal is to take this secret and to distribute it into shares S1 up to Sn, such that authorized coalitions can recover the secret and unauthorized coalitions learn nothing about the secret in an information theoretic sense. And the basic complexity measure is the total bit length of the shell. So we think about the secret as being a single bit secret, and the goal is to realize A with a minimal total shell size. And it's a very famous and well-known open problem in information theoretic cryptography to understand what is the best achievable shell size for a general n-party access structure. So let me tell you what's known about this problem. So since the late 80s, we know that this problem can be solved with complexity roughly 2 to the n, where n is the number of parties. And we have a lower bound which says that essentially the complexity is n squared. This is due to Silmas. The upper bound was due to Ito et al. And for a while, this was the state of the art until a few years ago, where Chimran and Vinod showed us that this can actually be improved. And the exponent can be brought down slightly below 1. So you can see the exponent here is a constant which is slightly smaller than 1. And following this result, there were several other improvements. And in this paper, we continue this line of research, and we improve the exponent down below 0.6. And in fact, as a nice bonus, we have here this constant has actually a very nice form. This is 1.5 to the power of n. So this is a natural complexity point. We also studied the case of linear secret sharing schemes. So in this setting, the sharing function of the dealer is a linear function, say over GF2. And here the picture is somewhat similar. So again, Julian and Vinod were able to improve the trivial 2 to the n lower bound, upper bound slightly to 0.999. And following this result, there were several improvements. And in this work, we get an additional minor improvement, and we can get down, we can reduce the exponent almost to 3/4. And here I should say that the gap between the upper bound and lower bound is not that large, because here we have a lower bound of 2 to the n over 2. So we know that the exponent cannot be below half. Good. So a few words about the main ideas. So in a very high level, the difference between our work and previous ones is that we focus on what we call up slices and down slices access structure. So let me explain what these access structures are. So first, let's order the sets in a lattice, where the empty set is in the bottom and the set of all parties is on top. Okay, and a K up slice access structure has the following form. So on level K, I'm allowing sets to take arbitrary values. So they can be authorized or unauthorized. You're allowed to specify exactly the structure here. Okay, no constraints. Below, right, smaller sets are unauthorized. And larger sets, well, they are authorized only if they have to. What do I mean by this? So if I'm looking at a set here, I'm going to define that it is authorized only if it is a superset of an authorized set of size K. Okay, otherwise I'm going to put here, I'm going to say that the set is unauthorized. And if you think about it a little bit, you'll see that this is equivalent to monotoke DNF, where all the minterms are of size exactly K. So these are up slices. And we also consider the dual version of this thing, which are down slices, and they correspond to CNFs. And what we show in our work is that first, we can realize up slices and down slices with the complexity that I showed you in the previous slides. And second, and this is actually an easy step, general secret sharing can be reduced easily to up slices and down slices. Namely, you can glue together up slices in order to realize a general secret sharing scheme with relatively low cost. So as I said, the first step is the non-trivial part, and here this is expensive, right? This is where the exponential complexity goes to, and for this we exploit previous tools and introduce new ones. And the second step is really trivial and very cheap. And it's interesting to compare this outline to previous works that were based on basically on slices. Okay, this is how slices look like. And in this, and in the previous frameworks, basically these slices were cheap to realize, based on work of Karen, Vinod, and Hotekui, but actually are hard to glue together. So this is exactly the opposite case compared to the current approach. Some other results in the paper. So we look at the random up slices, and the reason is that there's a very intriguing result from last year by Baimel and Fass, who shows that a random access structure are actually very cheap. They have a sub-exponential cost. And the reason is that if you choose a random access structure, it looks very similar to a slice function, and we said that this is easy. So we ask, is it also true for random up slices or random DNFs if you want? So we study several natural distribution over K up slices. I'm not going to define it here. And we show the following results. So first we show that at least given current techniques, we don't know how to realize this access structure with sub-exponential complexity. So this gives us the first candidate distribution for exponentially hard secret sharing scheme. Nevertheless, we can show some improvement compared to the worst case. So still we have exponential gaps between the worst case complexity and the average case complexity. And for this, we actually generalize an approach that was, again, used by Baimel and Fass for constant case. So for very low levels of up slices. And since they use constant case, they only got polynomial gaps, but we use linear case, and therefore we get exponential gaps. So now you can ask, is this gap real? Right? I mean, so this is the gap between the best known constructions, but maybe the best known constructions do not reflect the real true picture. So of course we cannot prove that this gap is real because we don't know how to prove exponential lower bounds for secret sharing. But what we can show is the following interesting result. We can prove unconditionally a gap theorem that says that there exists an exponential gap in at least one of the following cases. So either there's a gap between this worst case and the average case up slices, right? Worst case DNFs versus random DNFs, or there exists an exponential gap between access structure and their duals. Okay, and this is an interesting open problem whether the two are equivalent. This is a well-known problem. Or there exists an exponential gap between linear secret sharing and nonlinear secret sharing. And here I mean, when I say exponential gap, I mean that nonlinear secret sharing can go below this exponent of half. Namely that every function can be realized with an exponent which is 2 to the alpha n for some alpha smaller than half. So we don't know how to prove any of these separations individually, but we know that at least one of them holds. So to conclude, so we look at up slices, down slices. This seems to be like a useful and very natural families of access structure that deserve a further study. This is the new state of the art, 1.5 to the n versus quadratic, still a huge gap, and the obvious open problem is to try and narrow this gap. Thank you.
Okay. Thank you very much, Benny. Let's oh, I guess it does not work virtually. Okay, let's thank so let's go to the next talk because I don't think we have time for question. So let's immediately go to the next talk. The next talk is by Ronald Kramer, Mathieu Rambaud, and Xiaoping Xing. And the title is Asymptotically Good Arithmetic Secret Sharing over ZP L over Z with strong multiplication and its application to efficient MPC. Wait, wait, is there anyone here? Ronald Kramer, Mathieu Rambaud, or Xiaoping Xing? Oh, I see Mathieu Rambaud. Okay. If anyone has a question while Mathieu Rambaud is preparing to talk, please ask in Zulip or in the chat or raise your hand. Matthew, I think you're muted. I don't know if you want to talk. Oh, okay.
Matthew, your sound is not actually coming through. It says you're unmuted, but it does not appear to be working. You may need to log out and log back in. And Fabrice, if you wanted to move on to the next talk, and then Matthew can maybe figure out sound issues.
Okay, okay, it's okay for you.
Oh,
No, it's okay.
Oh, the sound is not very good.
Okay.
Okay, let's move to the next talk. If you can try to find better headphone or better, the sound is very, very bad. Better either headphone or speakerphone or something like this. Okay, so so let's move to the next talk. Large message homomorphic secret sharing from DCR and application. And this is a paper by Jasper Singh and Lawrence Roy. And Jasper is giving the talk.
Thanks.
Sorry to switch the program like this.
That's fine. Is my screen shared?
Yes, perfect.
All right. So hi, this is Jaspal, and today I'll be talking about our recent work on large message homomorphic secret sharing from DCR and applications. This is a joint work with Lance Roy at Oregon State University. So let's begin by defining what is HSS. So the traditional definition of 1 minus p HSS consists of 3 algorithms. The share function is used to secret share the input X with 2 parties. Each party runs the eval algorithm, which takes as input a share of X, and it also takes as input a program description P. The output of eval is fed into the decode function, which outputs P of X. HSS is termed secure if it satisfies correctness and privacy. Correctness ensures that the decode outputs the correct value P of X with probability at least 1 minus P. And privacy ensures that each share Xi individually hides the input X. In this work, we will consider the restricted multiplication program or RMS programs as the model of computation. In this model, each memory value is bounded by a parameter M, and it allows for the following operations. So you can initialize a memory value to 1. You can add 2 memory values. You can multiply a memory value by a constant, or you can do a restricted multiplication. That is, you can multiply an input with a memory value. Coming to our contributions for HSS. So in this work, we introduce a new HSS construction with negligible correctness error, P, and for exponentially large message spaces M for RMS programs based on Damakart-Zurich encryption scheme. An HSS that fails with negligible error was previously only known to be based on LWE assumptions, whereas our construction is secure assuming the DCR assumption as well. Unlike all previous works, our construction does not rely on any circular security assumption or on a circular secure encryption scheme. I will also note that a concurrent work at Eurocrypt 2021 achieved similar results, but they based their construction on Pi-A instead of Damakart-Zurich. You can find a more detailed comparisons of our construction to theirs in our paper. Next, I'll present a general framework for the design of HSS constructions. So HSS is based on the interplay between 2 encodings, an additively homomorphic encryption scheme and an additive secret sharing scheme. Encryptions hold the input to the HSS program. Hence, the share function on input X outputs the encryption of X to both the parties. The additive shares represent memory values of the RMS program. We say that a value Y is stored in the program if the parties have additive shares of phi times Y, where phi is the private key of the encryption scheme. Both are additive homomorphic schemes, hence given encodings of X and Y, we can generate encodings of X plus Y and a constant times X. We will now look at how an HSS scheme evaluates each RMS operation given the encodings that we defined. To initialize a memory value with 1, the servers can use additive shares of phi, which will be given to them as outputs of share. To output a value X, the decode function can subtract the additive shares of phi times X and divide it by the private key phi. The addition of memory values and multiplication by a constant comes for free by the properties of the additive shares. So the key challenge that remains is in how we perform the restricted multiplication. That is multiplying an input X with a memory value Y. And this is essentially where all HSS schemes differ. So we next look at how we propose to compute this RMS multiplication. So in our HSS construction, we use the Damagard-Zurich public key crypto system. This public key crypto system is based on the homomorphism exp and its inverse function log as shown here. Note that these are finite sums in modulo n to the s plus 1, and both these functions are efficiently computable. We can use these homomorphisms to define the encryption scheme. Particularly note that the encrypt function applies the homomorphism x on the input x, and it multiplies it with a random perfect power of n to the s. And the decrypt function has two key steps. It first exponentiates the ciphertext with the private key phi, and then the plaintext is extracted using the log function, which is the inverse of exp. Coming back to the problem of RMS multiplication, we solve it as follows. Each party locally raises the encryption of X to their additive share of Y. The parties hence end up with multiplicative shares of encryption of X times Y raised to the power phi. Here we define multiplicative shares of Z to be elements Z1 and Z2 held by the two parties, such that Z is Z1 by Z0. Since the first step in the decryption algorithm involves exponentiating by the private key, which we have already performed here, the challenge is now to convert the multiplicative shares of X of phi times XY into additive shares of phi XY. For this, we use something called the distance function. So if both parties evaluate this distance function on their multiplicative shares of X of Z, then by definition of the distance function, they would output additive shares of Z with probability at least 1 minus epsilon. So this completely describes how an RMS multiplication can be carried out using the distance function and the properties of the additively homomorphic scheme. Our key insight in this work is in that we designed the distance function for Damagard-Zurich ciphertext such that the epsilon error is negligible, which was previously not known based on any DTH or DCR-based HSS construction. Specifically, we propose the following distance function, which is log of C divided by C modulo n. Using the properties of log and exp homomorphisms, we show that this function is well defined and that it's correct. You can check out the paper for a detailed proof, along with the discussion on when exactly the distance computation fails with negligible error. For final remarks, I'll share that I couldn't discuss all the results we propose related to HSS in our paper. Particularly, I didn't get to discuss our new HSS definitions, our two applications for HSS, particularly oblivious RAMs and trapdoor hash functions, and also a modified HSS construction that satisfies additive decoding. You are welcome to check out a paper to see all the details. Thank you.
Thank you very much, Jaspal. Any questions? Somebody. Okay, so I have one question. So you said that your paper is based on Damagard-Zurich. Since Damagard-Zurich is a generalization of Paillet, does your paper also apply when instantiating using Paillet, or you need a higher order in the Damagard-Zurich?
That's a good question. So our scheme actually works for Paillet as well. The only disadvantage is that to encode an input to the RMS program, if you're using a Paillet encryption scheme, you would have to break it into multiple ciphertext of Paillet to encode a single input of the RMS program. But whereas if you are using Damagard-Zurich, you can expand the plaintext space to be large enough. So that is helpful to encode a single RMS input using a single ciphertext of Damagard-Zurich. But yes, the distance function that we propose sort of it has negligible error probability for Paillet as well.
I see. Let's see. Okay, so I guess we are back on time. So thanks, Jaspal. And Matthew, are you ready to join? Let's see.
Matthew, you'll need to unmute if you can.
Yes, is it better now?
Yes, much.
Yes.
Okay, fine. So
Okay,
if you allow, I can.
Okay, perfect. So let me introduce you. Sorry, I realized that I didn't. So it's a paper that we talked before, like the second paper of the session, asymptotically good arithmetic secret sharing over Z P to the L with strong multiplication and its application to efficient MPC. And this is a paper by Ronald Kramer, Mathieu Rambaud, and Xiaoping Xing, and Mathieu is giving the talk.
Thank you very much. So the take-home point of this paper, the technical content, is that we consider gadgets for information theoretically secure computation, which were previously known over finite fields. And we carry them over rings Z modulo P to the LZ with exactly the same parameters. The interesting case is where P equals 2, because then it is the ring of machine integers. These multiplicative gadgets, apart from the one in the title, which is secret sharing, are reverse multiplication friendly embeddings, which I recall are useful to amortize the cost of many evaluations in parallel of the same circuit. And the third gadget is the batch verification of multiplicative triples. So you have a batch of shared triple, and you want to check if they are indeed multiplicative. For this last one, we, of independent interest, improve its complexity even over finite fields. So we recover as a particular case a previous result on the complexity of MPC over field. So the general motivation to study this gadget, the big picture, is the secure computation of arithmetic circuits which are naturally expressed in the ring Z modulo P to the LZ. So circuits with additions and multiplication gates modulo P to the L. And we ask the question, what is the complexity of protocols to directly compute in this ring? And as a corollary of our result, we close the gap between the complexity of secure protocols over rings and previously known complexity over fields. Now, the first gadget, which I'm going to define again, is secret sharing with strong multiplication. It asks that if you have two vectors of shares of one secret S and one secret S prime, and you don't know the vectors of shares, but you know products component by component, product share by share. You know many product Si, S prime I. Then the strong multiplication property states that even if you are missing some of these products, you miss T products, then anyway you can reconstruct the product of secrets from the n minus T remaining products. So the technical hurdle to achieve this primitive over rings is the following. The technical problem is to find codes with small square. Why small square? Because a square of a code, it's the code generated by all the products of code words component by components. Small square means big distance, means you can reconstruct a product of two secrets from a few coordinates. This is what we are looking for. The problem is that, in general, the square of codes over rings, they are very big. So even if you start from a code over a field which is known to have a small square, it is not guaranteed at all that if you lift the coefficients of the code modulo P to the L, then you take the square will be very big. Let me give the intuition of this problem. This problem comes from the fact that when a code has a small square, it means that you have many linear relations between the products of code words. But these linear relations, they hold modulo P. It is not guaranteed at all that these relations also hold modulo P to the L. This is the big technical problem. So the main theorem of the paper guarantees the existence of codes with small square over rings. Unfortunately, it is not needed to understand the proof to construct them explicitly. The explicit construction starts from the intuition that I've just said. The intuition is that you start from a code over fields such that the products component by component, the square, they have many linear relations between them. The square is very small. And from this ingredient, you would like to construct the same in a bigger ring, modulo p to the L. So the explicit method that we develop in the paper, which is called as the Hansel lifting method, is that we write down the linear relations between square of elements of the code, and we lift them recursively, modulo PL plus 1, so that in L steps, applying every time a linear system over Z modulo PZ, a finite field, we achieve to find a code over a big ring with a small square. This concludes my talk.
Thank you very much, Mathieu, and thanks to all the speakers before the break. Do anyone have questions about this talk or the previous talk? Please raise your hand or write in the chat or write on Zulip. Oh, Watson Lad asked to Mathieu, can we see your result as an analytic one for p-adic codes?
No, sorry, it's not for Mathieu, it's for a previous talk. Sorry, no. Okay, sorry, no, not.
Absolutely. So it's a very interesting question. It is true that all our results that I presented modulo p to the L, they also hold they also hold in the p-adic ring. So the infinite ring, the p-adic numbers with infinite p developments. But to have these results, you need more ingredients. So in the paper, we only presented it over finite rings, Z modulo a fixed p to the L.
Okay, thanks. And Anat Paskin-Cherniaski, sorry for the name, is asking to Benny Applebaum, do you think looking for a different family of functions that achieves a better trade-off between shear complexity and gluing complexity is a viable way for improving the upper bound for general secret sharing?
I wish, I don't know. I mean, frankly, in this field, I currently don't really trust my own intuitions, and we've seen all sorts of surprises in the last few years, and maybe I think that it's possible. I don't even know whether to guess that there is a sub-exponential solution or not. So I don't know. It's certainly possible that such an approach would work.
Okay, any other questions? Okay, so then we'll reconvene in 10 minutes at 3:20 for the second part of this session.